Alright, welcome back to what's going to be the main part of our lecture today, understanding the vertical structure of the atmosphere. What's going to be happening here is we're going to be describing features of the atmosphere in terms of how they change with height. This expression with height, or with respect to height, means like as you go up in the atmosphere. So how does temperature change with respect to height? That means as you go up in the atmosphere, how does temperature change, or how does pressure change, or how does moisture change, or whatever. Now, there's going to be a lot of different ways to describe this vertical structure of the atmosphere, and today we're going to be talking about it in terms of like how pressure changes with respect to height, and how moisture changes with respect to height, and how temperature changes with respect to height, although in practice we don't actually do much about how temperature changes with respect to height at this point in the course. Rather, we're going to be focusing on something called the environmental lapse rate, and how the environmental lapse rate changes with respect to height. And then finally, how the chemical composition of the Earth's atmosphere changes with respect to height, like as in the mixture of the gases that make up the atmosphere. Alright, so first of all, how about how pressure changes with respect to height? Well, in order to understand how pressure is going to change as you go up in the atmosphere, you need to understand an important little detail about how we can think about pressure. Now, we're going to have a lecture in the second module, of course, that really goes into a lot of detail about how pressure works in the atmosphere. But for the purposes of what we're doing now, it's enough to know that you can think of pressure as the weight of the air above you. I mean, air has mass. We don't often think about a lot of weight to air, but air has mass. It's experiencing gravity, so it has weight. And pressure, the pressure that you're experiencing from the air, is just the weight of all that air above you. Alright? Well, as you go up in the atmosphere, as you go up a ladder, there's going to be less air above you than there was when you were at the bottom of the ladder, right? Because now some of the air that had been above you is now below you. So pressure can only do one thing. It can only decrease with respect to height. And if we take a look at a graph of a typical way in which pressure changes with respect to height, you can see how it starts down near the surface, near a pressure of about 1,000 millibars. We'll learn a lot more about the units of pressure and so on in Module 2. And then it decreases, getting closer and closer to zero as you go up with respect to height. In fact, it decreases at a very interesting and very specific rate. For every 5.6 kilometers that you go up in the atmosphere, the pressure is half of what it was at the lower level. So for example, if the pressure at some height of, let's say, 6 kilometers was 490 millibars, if we could read it off the chart there, well, if we went up 5.6 kilometers there to 11.6 kilometers above the ground, the pressure would necessarily be half of what it was at the bottom of that layer. So if it was 490 at 6 kilometers above the ground, then at 11.6 kilometers, it has to be half that, or 245 millibars. This is actually a pretty sneaky and neat little rule, and you're going to use it in the ATS 114 lab to learn a little bit more about the distribution of pressure in the Earth's atmosphere. How about moisture? How about the amount of moisture in the atmosphere? Now, again, I think it's in the third module of the course. We actually spend a couple lectures talking about the details about moisture, how we measure it, the units for it, and so on in the Earth's atmosphere here. But in order to understand how we can talk about how moisture changes with respect to height in the Earth's atmosphere, we need to be able to think about moisture in terms of the source of moisture in the Earth's atmosphere and the sink of moisture in the Earth's atmosphere, remembering those terms from our first lecture in this module. Well, what adds moisture to the Earth's atmosphere? Hopefully it's not a huge surprise to you. What adds moisture to the Earth's atmosphere is evaporation off the surface of the Earth. Evaporation changes liquid water that's on the surface of the Earth into a gas that is now up in the atmosphere. So the source of moisture for the Earth's atmosphere is evaporation. The sink of water vapor, what is removing water vapor from the atmosphere and turning it back into a liquid, is condensation in clouds. So when clouds form, they change water vapor that's in the atmosphere back into little droplets of liquid water. They take the water vapor out of the atmosphere to make clouds and eventually raindrops and so on that take that water back down to the ground. But notice that there's an important difference here. There is the source of water vapor and the sink of water vapor are at two very different places. The source of water vapor is down at the surface, and the sink of water vapor is up high in the Earth's atmosphere. And that's going to tell us something very important about the distribution of water vapor in the Earth's atmosphere. But it's a little hard to think of when you're thinking of just humidity. You kind of need an analogy first. So first, let's talk about swimming pools. Here is a big, crowded swimming pool, and we're going to use this as a way to understand about water vapor in the Earth's atmosphere. Now I have a huge pool here. Now let's suppose way there on the far end of the pool, that's like the shallow end of the pool or whatever, and that's where all the little kids are, okay? So all your little kids are over at one end of the pool, and let's say this is, I don't know, the deep end, or the lifeguards say all the big kids have to stay over here, and so the big kids are at the end of the pool that are closer to us in here. Alright, now just having that information here, let's say what you were worried about is about pee in the pool. Alright, you're very averse to pee being in the pool. Don't go into pools if you're worried about pee, let me tell you. As a father of several small boys, let me tell you, don't go in pools if you're worried about pee. Anyway, well, alright, if we're going to think about pee in the pool here, well, one end of this pool is going to be a lot worse than the other, right? I mean, if the little kids are over there on the far end of the pool, well, they're the source of pee. Presumably, that's where most of the pee is coming from. Just like on the surface of the Earth, the water vapor is coming from the surface of the Earth. This is the end of the pool where the pee is. And the big kids on the other end of the pool are hopefully not a source of pee. And maybe we could even say on the big kid end of the pool, maybe there was like a filter or something that was removing the pee. So like there's a sink of pee. The water actually gets more pure over there on the big kid side of the pool. Alright, so, you know, we got some kind of filter or something over there on that end of the pool. Well, what we'd be establishing then is like a pee gradient, right? There'd be a lot of pee on the end where the source of pee is, namely the little kids, and there'd be basically no pee over there on the closer end of the pool where you know, the filter's removing pee or whatever. There's a high concentration of the material that we're interested in, the constituent that we're interested in, namely urine, on the end where the source of the pee is. And there would be a smaller amount of pee on the other end of the pool where there's being removed. Well, this tells us very much what's going on with regard to water vapor in the Earth's atmosphere. I mean, we know that the source of water vapor is down at the surface, and what's removing the water vapor from the atmosphere, namely the formation of clouds and rainfall and so on, happens up high in the atmosphere. So therefore, we should expect the water vapor concentrations in the atmosphere to be greatest near the surface, and to tail off towards zero the higher up you get into the Earth's atmosphere. Now this diagram that I have on here is a little bit technical. It has a lot of plots and so on here, but basically they're all just showing examples of how moisture changes with respect to height in different environments and so on. And what I want you to notice is all of them have the greatest amount of moisture down near the ground at heights of like 0 kilometers up through about 5 or 6 kilometers, and then the water vapor in the Earth's atmosphere is decreasing farther and farther up you get in the atmosphere. So we can say pretty convincingly that most of the time water vapor in the Earth's atmosphere decreases with respect to height. Now before we move on to the other stuff that I want to talk to you about with regard to vertical structure of the atmosphere, let's do 3 more quick questions. Question 4. Pressure never increases with respect to height in the atmosphere because pressure is the blank of the air above you. A, weight, B, temperature, C, trick question, pressure always increases with respect to height, or D, trick question, pressure can increase with respect to height. Oh. Which was the right answer there? Make a choice from those 4 options and get a little feedback before you move on to question 5.